Assalamualaikum warahmatullahi wabarakatuh, and good day. So now this is PMM 1533, strength of materials. We meet again today for today's lecture with title torsion. So by right, we are already in chapter 2, which is new chapter, and the objectives of this topic is to analyze the circular and non-circular members problems which are subjected to twisting couples or torque. And the following item listed here is the lesson objective for this subject. These are the examples of structures subjected to torsion. You can see what will happen to the bar itself when the torsion loading being applied onto that component. For example, this one is for pump and this one is for pulley system. On this figure, you can see the types of failure happens when torsion loading being applied onto the shaft. And this one will happen to structures made by wood. You can see the failure occurs on the wood. So by right, for torsion, the formula that you need to know and remember is tau equals to TR over J. J represents for polar moment of inertia. C or R is for radius for the circular members. Pi R power of 4 divided by 2 for solid circular shaft. And for hollow shaft, J equals to pi over 2 times with R outer power of 4 minus R radius inner power of 4. So all these formula need to be remembered. This is what will happen to the circular members whenever the torsion loading being applied to it. You can see the concentration of stresses for the circular members. This one for solid shaft and this one for hollow shaft. So through this one, we can determine the formula for shear due to torsion, which is tau equals to TR over J, or T rho over J, or TR over J. C rho or R is actually represent the radius of the circular members. And you see torsion not only being applied to circular members only. There are other shapes other than circular, which is rectangle, triangle, semicircle, quarter circle, ellipse, and so on and so forth. And if you notice from this table, this one use R instead of C in calculating the value of polar of moment inertia. This table can be found in your reference book. Okay, so now let's move on to example number 1. Let's read it together. The stress distribution in a solid shaft have been plotted along 3 arbitrary radial lines as shown in figure below. Determine the resultant internal torque at the section. So the radius is given to you with R equals to 50 mm, and shear stress is also given to you with a value of maximum shear stress equals to 56 megapascal. And the question asks you to find the torque at the section. So we know that the formula for for tau shear is TR over J, and from there we know that you need to find the value of J, and R is given. So J is polar moment of inertia for the cross-sectional area given. J just substitute into the formula, and we know that this is a solid shaft, and therefore J equals to pi R power of 4 divided by 2. After that, substitute into shear formula. Tau max equals to TR over J. Tau max is given, which is equals to 56 MPa, and then just rearrange the formula and you get the value of torque, which is equals to 10.995 kilonewton meter. So that's how you calculate the value of torque by using the formula of shear due to torsion. Now let's move on to example number 2. Let's read it together. A hollow cylindrical steel shaft is 1.5 meter long and has inner and outer diameter respectively equals to 40 and 60 mm. Find the largest torque that can be applied to the shaft if the shearing stress is not exceed 120 megapascal, and B asking you to find the corresponding minimum value of the shearing stress in the shaft. Okay, question A. Let's collect all the information given. Tau max is given, which is equals to 120 megapascal. R2 equals to 0.03, R1 which is equals to 0.02. From there, we know that it is a hollow shaft, and then you need to use polar moment of inertia for hollow shaft, which is J equals to pi over 2 R outer power of 4 minus R inner power of 4, and eventually you'll get J equals to 1.021 times 10 power of negative 4 m power of 4. And we know that the formula for shear is TR over J. Rearrange it back, and then from there just substitute all the information, and you'll get the value of torque equals to 4.084 kilonewton meter. Now move on to question B. It asks you to find the value of tau minimum. For tau minimum, the formula is tau min equals to R inner divided by R2 times with tau maximum, shear maximum. So just rearrange the formula and substitute all the information given in the question, and you get the value of tau minimum, which is equals to 80 megapascal. Okay, so far so good, yeah. Now let's move on to example number 3. The shaft shown in figure below is supported by 2 bearings and is subjected to 3 torques. Determine the shear stress developed at points A and B located at section AA of the shaft. If you refer this figure, this is cross section of AA, so by right we are focusing on this section. Okay, and for point A and point B, this is the location of point A, and this one is location point B located along the shaft. So now let's look at the solution for this example. We know formula for shear stress is tau equals to TR over J, and first of all we need to draw the free body diagram for the for the AA section. From there, because we want to find the value of internal torque at cross section A, so taking moment in x-axis direction equals to 0, clockwise is a positive value, so you'll get the value of torque equals to 1250 kilonewton mm. And the value of shaft for solid shaft is j pi over 2 r power of 4. From there you'll get the value of j there. After that, since the question asks you to find the value of shear, the value of the question asks you to find the shear stress at point A and point B. So by looking at this diagram, at point A, radius is equals to 0.075 times 10 power of -3. And a formula for shear is TR over J for point A. So substitute all the information into this formula. So you'll get shear at point A is equals to 1.886 megapascal. After that, same steps. You need to check the radius for point B. So from there, we know that R equals to 15 mm. Substitute into the same formula at point B. So you'll get tau at B equals to 0.377 megapascal. Now let's move on to example 4, which is a little bit complicated. Shaft BC is hollow with inner end diameters of 90 mm and 120 mm respectively. Shaft AB and CD, this one AB and CD, are solid of diameter D. For the loading shown, determine the minimum and maximum shearing stress in shaft BC. And question B asks you to find the required diameter D of shafts A, B and CD if the allowable shearing stress in the shaft is equals to 65 megapascal. Okay, so please be aware that for this diagram, A, B and CD shaft are solid, whereas for BC here is hollow. Okay, so cut sections through A, B and BC and then perform static equilibrium analysis to find torque loading, or basically in other words, you need to draw a free body diagram in order to find a reaction force, reaction torque acting on AB section. So by taking moment in x-axis, you'll get T torsion at section AB is equals to 6 kilonewton meter. And this one, the value of torque here equals to torque CD, if you notice, because the value torque at A is the same as torque reacting at D. You see, basically the cutting section is the same as in the previous lecture. So if you do not understand on how to cut the section, then please refer to the previous lecture. Now let's move on to section BC here. Draw the free body diagram, the whole free body diagram, starting from point A until exactly before point C. So you'll get this free body diagram. And from here, we need to find the value of reaction torque at BC. So taking a moment at axis direction, positive value is clockwise direction, and you'll get the value of torque BC equals to 20 kilonewton meter. After that, we know that shaft BC is hollow, and therefore you need to apply moment of inertia for hollow shaft, and substitute all the information or the data given. You'll get the value of J, which is equals to 13.92 times 10 to the power of -6 and power of 4. And then The question asks you to find minimum and maximum shear at shaft BC. So tau equals to TR over J. For tau max, it's acting on the outer part of the shaft itself. So tau max equals to TBC times outer radius of the hollow shaft divided by J. So substitute all the information given there. You get tau max equals to 86.2 megapascal. So the outer parts will suffer the maximum shearing stress as compared to the inner parts of the shaft itself, no matter whether it is hollow or solid. After that, you can either using the formula tau min equals to TR over J, or you can use this formula, which is tau min divided by tau max equals to R1 divided by R2. By right, you should get the same value of tau minimum. If let's say you want to use TR over J, tau min equals to TBC R inner divided by J. Alright, or else you can use this formula, and tau min equals to 64.7 megapascal. After that, the question asks you to find the diameter of the shaft. So we know that tau equals to TR over J. Okay, and then hold on, let me check the question. Okay, you need to find the diameter for shaft A, B and CD. Alright, so tau maximum is 65 MPa. This one is given in a question, and then just substitute all the information there, and the torque is also known with equals to 6 kilonewton meter. From there, you'll get the value of R, or C equals to 38.9 times 10 power of -3, or the diameter, which is equals to 77.8 mm. Okay. Enough with the example, because I have gave you a lot of example for talks for this topic. And from there, please do exercise 1, and you need to submit this exercise before 4 o'clock by today. So with that, thank you very much. We'll see each other again for the next lecture. Okay, bye bye. Thank you.